Okay, my good friends, we are in for a wonderful time today. This is going to be a little lengthy, but it should be wonderfully entertaining. It will be to me. I have just been alerted to look this. Is this a new kind of physics? This is the Royal Institution of London, this is where Mendeleev made his presentation of the periodic table. So this goes back a little ways to this particular place. They think they really got it covered, and they pretty much do for what is currently accepted. However, is this a new kind of physics? And yes, it absolutely is. Now, he's at CERN, which is in Geneva, and I took particle physics at the University of Geneva, so I have some understanding there, and they saw my research. I presented it to them several years ago, and they were interested, but that was about as far as it got. Now, I am going to show you how far we got, and then we're going to see how far they got. All right, as crazy as it sounds, cosmic rays can be picked up by smartphones, and they can do the same thing as the multi-million-dollar observatories. And cosmic rays are energetic, subatomic, means smaller than the nucleus, particles created, scientists think, in cosmic accelerators like black holes, exploding stars. Now listen to this very carefully. When the particles crash into Earth's atmosphere, they create showers of secondary particles called muons. That is exactly what we found, I believe. So Royal Institution wants to know if we're talking about new physics, and yes we are, because this is a particle, and this was a wave. That particle that was in that wave has a big magnetic field around it, and we sucked it through this venturi and separated the particle from the wave. Then we exploded the particle, which had black and white, and it turned into a shower of particles, and the black particles, which are the muons, came around. So that is my statement, my claim. And here is what happened at the venturi itself. The black particles walked away from the white particles, and the black particles and the white particles were separated just a minute ago until they crashed into the venturi. This was the particles as they come through the air. And we can see these with these smartphones, so don't tell me you can't see them. And the reason we can see them is because they're so brilliantly illuminated with radiance. That's all. CMOS does not discriminate. If you can put out enough electrons and stimulate that complementary metal oxide semiconductor material, it will pick it up and it will amplify it and it will show it. And those particles are light, and those are photons, and they're two dipole electrons. Each one of them is an electron back to back. And when they hit the venturi, they literally decompose into separate particles right there. All right, let me back out of here so it makes more sense. Coming in, you can't even see them. Coming in, they just have really no definition. As they stack up, they display exactly what they're constructed of, and then they explode, because you have to tune the venturi to be just the right size that'll let the white through but not the black, because the black is much heavier than the white. So here we are at the venturi, the black separated from the white. Exactly what CERN wants. They want to see the black with the muon just stay the muon, the black ball. And they want to see the white ball turn into a white shower. That's exactly it right there. So let's see what they came up with. And you saw what I can present. That was what our end result was. This 6 years ago, this was the end result. And I posted all about this, and I was going to the University of Geneva at that time for particle physics, and we discussed it there. And I presented it virtually everywhere in the world. And then it sort of just dropped. And now they're discovering some new physics. Let's see what they did come up with. Okay, my friends, so here we are back at the Royal Institution, and they have over 1 million top world geeks on this site, because that's what they do. They did very serious research. Look at all of this stuff: super black massive holes, the brain, self-assembling brain, mass. I mean, this is all the stuff that I love. So I watch all of their stuff, and let's see what they have to say about their new kind of physics.
on the Swiss-French border. And what the LHC does is really quite simple and brutal. It essentially accelerates subatomic particles called protons around this 27-kilometer ring, accelerates them to enormous energies, and then they're smashed into each other inside gigantic particle detectors, which are referred to as the experiments. And there are 4 of these detectors at CERN, but this particular result comes from the one that Paula and I work on, which is called LHCb. And this is a picture of the detector underground, just outside the town of the French town of Verney-Voltaire in France. And it's essentially a gigantic 3D digital camera whose job is to record what happens in these high energy collisions produced by the Large Hadron Collider.
I just want to make one point. It's just a large camera, and that's exactly what we're using, but it's small. But we don't have to be large because we're just looking at photons and light.
So to understand what LHCb does, I'm going to have to give you a very quick introduction to particle physics, just take you through the basics. So hopefully you're aware that everything in the universe that we know about, at least, is made of atoms. And as we all learn in school, atoms are comprised of particles called electrons, these negatively charged, as far as we know, fundamental particles in orbit around a central nucleus. And if we zoom in on the nucleus, we discover that inside the nucleus there are smaller particles called protons and neutrons. And if we zoom in even closer, we find that protons and neutrons are made of even smaller particles called quarks, which are represented by these little triangles in this image, which are held together by particles called gluons, which are particles of a force called a strong force, which is...
All right, let me just cut right to the chase before they continue on here. I claim that everything is made out of electrons, and I showed you those back-to-back little dipoles. Everything is made out of, let's call them bar magnets. That's all they are. And I knew this 50 years ago. This was a paper I did 50 years ago that was my final paper on the nature of virtually everything of matter. And everything was made of electrons. Everything had to be a dipole. There was no such thing as a single polar, gigantic, solid positive nucleus and tiny little electrons. They just pop together. Now, I did a video showing my credibility because I go back 50 years on this. I was in nuclear missiles when I was in the Army in 1968, and after that, I've been in semiconductors and all that stuff my whole life, so it's not something I don't understand. Now, with electron flood theory, it changes everything in physics. New physics, yes, 100%. So these kind of forces they're looking at are nothing more than the attractive forces of that black ball being gravity and the white ball being push to shove. I call it the push to shove, because you go up against another white ball and it's going to push you away, and you're going to shove it in, it's going to shove you back. All right, so let's go back and see what they have to say about what they discovered in new physics. Okay, so let's go back to here, where originally they used to say there was protons and neutrons in the nucleus, and that was it. And they were particles made up basically like big gigantic particles like this. Proton has a positive charge to it, so that it wants to attract an electron, basically. A neutron has no charge, and it is one electron bigger than a proton. That's all it is the mass of one electron. Now, I say the proton is nothing more than this right here, 1,839 electrons. 1840 make a neutron, and every electron is a dipole. It has a positive and a negative. It makes it basically a little bar magnet. So let's continue on what they have found.
Of even smaller particles called quarks, which are represented by these little triangles in this image, which are held together by particles called gluons, which are particles of a force called a strong force, which is essentially the force that's responsible for holding these quarks together inside protons and neutrons. So we have this rather simple picture, really, of what the universe is made from, and this is brought together in a really a stunningly successful theoretical framework known as the Standard Model. And the Standard Model is really the closest we have at the moment in physics to a theory of everything. It describes all the matter that we know about in the universe, at least all the matter that we can observe directly. And it describes it in a relatively sort of economical way. So you have the fundamental particle, the electron, that goes around.
All right, that's the fundamental particle that constructs everything there is. There is nothing but an electron. However, an electron has a positive and a negative charge. So it's not just a negative charge. And they have never seen these. I showed you the electrons, and I showed you the electrons actually dividing the positive from the negative charge. And that's dark matter from light matter. I never realized that was possible, but we saw it. And I want to show you right now, it's fission and it's fusion, and we can get free power right now. And this is why they're looking for these muons and so forth, because you saw they were attached. They made fission right here. That's fission. The black ball is away from the white. That's no question. That is fission. It went through the accelerator, came back together, and they fused back together. That's fusion. That is exactly identical to what happens in fission electric generation right now. They break apart particles, but they're using big stuff. We're just using light. We can't run away. We can't overheat. We can't cause any destruction. We're just changing. They're using protons and big chunks of particles. When they break them apart, they're just very, very destructive. We're breaking apart light, which comes right back together in a very confined little region. And in between, though, there should be a ton of extra energy, and you can see it, and they know about this. So I'm saying fission, fusion. All right, that is exactly what they're looking for right now, and that means free power. And it is exactly what they say right here. There it is. There's the muon, and there's the electron shower. You can't get any more clear than that. All right, like I said, this could take a little while, but I want to get this finally understood so we can get somewhere here. Now, we're back to where they think these different charges are holding these gluons and so forth together. Now, let's keep it going.
Particles of a force called a strong force, which is essentially the force that's responsible for holding these quarks together inside protons and neutrons. So we have this rather simple picture, really, of what the universe is made from, and this is brought together in a really a stunningly successful theoretical framework known as the Standard Model. And the Standard Model is really the closest we have at the moment in physics to a theory of everything. It describes all the matter that we know about in the universe, at least all the matter that we can observe directly. It describes it in a relatively sort of economical way. So you have the fundamental particle, the electron, that goes around the outside of the atom, and then you have these two types of quark, the up quark and the down quark, and they make up the nuclear material in the atom. And that's it. So you and me and everything in the world around us is really just made of combinations of these three particles arranged in a variety of different ways.
The reason I was showing you all those little doodles is I did all those, and I presented a plausible opposition to that theory 50 years ago, and I was crushed. So I went on my own and had my own business, but this should have been solved a bazillion years ago, and now it's new physics.
Now, these aren't the only particles in the Standard Model. There's also something called a neutrino, which is often referred to as a sort of ghostly particle because it doesn't interact with ordinary matter very much. There are actually trillions of these particles passing through you every second. They're produced by the sun in huge quantities, but they don't interact with matter very much at all because they don't have any electric charge. And then in addition to these four particles, there are additional copies of them that come in two further columns. So this is what we call the second and third generation of matter. And in each of these generations, there are basically identical copies of the first set of particles with the same properties but different masses. So for example, the electron has a sort of heavy version called the muon, which is...
Right, exactly. The electron has the muon. That's the black ball and the white ball. This was 50 years ago. Transfer of energy from light is to atomic vapor. I wrote this, dipoles. Everything is dipoles. And I wrote this 50 years ago. And then I've been fighting ever since. And then, 7 or 8 years ago, a friend did some light experiments, and we started to see these particles show up with these new cell phones. And from there, it's been unbelievable. Now we have them that can show field effects that's just stunning. Anyway, I'm going to continue on. They're showing all kinds of different little bits and pieces because when they hit their particles together, they're using 100 billion times more particles than we are. We can see the actual individual particles. We can see them divide as you saw. We can see them come back together as you saw. That's fission as a division. Fusion is when they come back together. That is power generation in its supreme simpleness. And it's being avoided because they just can't accept somebody outside of their realm speaking about these things. And I've been speaking about them for 50 years, but I've been outside their realm. And it's very hard to get anybody to even talk to you about it, no matter how much evidence you have, which I have all the evidence. So here we go.
Is identical to the electron in every way, but has a mass about 200 times larger. Now,
there you go, right there. We increased the interaction 200 times. That is the key to this whole thing.
That's going to be an important thing to remember when we get a bit further into the event. There are also a bunch of forces in the standard model. There's the electromagnetic force, which is carried by a particle called the photon, and that's a force where a lot of work was done on that, understanding the electromagnetic force at the Royal Institution by Michael Faraday in the 19th century. And then there are two other forces, the weak and the strong forces, which are the strong force responsible, as I said, for holding quarks together in the nucleus, and the weak force responsible for basically when particles transform from one type into another. So when particles decay, it usually takes place through this weak interaction.
Let me just go explain these forces in electron flood theory. Okay, don't forget, this is our new physics. Each side of this is an electron. That's the explosive part. That is the muon part, which is the black, and I think it's dark matter. Now, here's what normally would happen coming through the air would be the pulsed red laser. That's where that particle sits right there. But it has a field surrounding it which is literally enormous for that size of a particle. Because one hydrogen atom has 21 centimeters around it that it controls magnetically. So think about that. Now, we're 1,839 times smaller than that. So it's, I believe I've calculated out to be like 0.002 inches or something like that. But there's a certain diameter, a certain width that is the field that that particle will control. And you have to restrict that width so that that particle has to force its way through, and that's what we did, which created the excitation, or the acceleration, I'm sorry, which is also the excitation. And what happened was that wave began to elongate because the particle is being accelerated, which is not allowed for in the standard model. And it is a particle, it's not a wave. We saw it as a particle, so that's not something we can really have to discuss a lot about. We can see it's accelerating, that's not a big stretch. We can see it crashed here, there's no question about that. We can see a total huge increase in energy from the energetic value here, which is the 200 times, I would agree with that. And we can see that it completely radiates this whole entire area so extremely violently, because these are more particles of light which you'd never see, but they're being so impacted backwards by what's called reverse EMF, reverse electromagnetic force. And that's it right there. I don't know if you can pick that up on a camera, but there's all these little lines coming back from this reverse concussion. And of course you have the fusion here, and you have the what they call the interference patterns. Those are separation patterns, because this is a single slit, and it's a venturi, and this particle spins. It's a magnetic particle, all right, and it sits on it's just like this, it spins. And sometimes it goes that way, sometimes it comes over, it goes this way. Most of them go through the center, but it is a spinning particle, and these particles will not get next to another particle like itself, as a white particle, because these are all the white ones. And the white ones won't be next to each other white one, obviously, they're exploding. The black ones couldn't care less. They want to be next to everybody. The black ones are minglers. They just want to grab a hold and pull everything together, and they are much more attractive than the white ones, apparently, and they get out of the way of this interaction. These are the Higgs fields, and this is the way the particles spin. Now this is the blue, which is you can't really see the particle, but you can see it spinning to the right, drifting to the left, expanded, concussed. That's slowing down. So we know we can speed them up, We know we can slow them down, and we know when they impact, they separate. And here's the separation. That particle of black and white is separated. It is now apart, and that is 100% white. That's the white balls only. There's no black there whatsoever, not a tiny taste. And now they're trying to grab back to the white ones, exactly at this distance, exactly right there. So either we harvest it right there or back here somewhere, but we need to grab a hold of this energetic value, and that is the increase that they're looking for free energy, as far as I'm concerned. This is fission. We broke the particles apart. That's fusion. They came back together. That is nuclear power. And once again, CERN knows this, Geneva knows this, everybody knows this, Fermilab knows this. I'm showing them the exact same things, and I've been showing them for years, so I am a little frustrated, but let's see what they came up for their new physics, because I haven't seen a video yet. We're looking at this at the same time and going to discuss what they have to say. And that's what I'm doing. I'm going to cut in every time they have something to say that I can present evidence to support my side of it. All right, so let's just look at this standard model again. And he's claiming this is all very, very successful. Well, it's not, and they know it's not. They just have nothing to replace it with. Electron flood theory replaces it with nothing but electrons.
To these four particles, there are additional copies of them that come in two further columns. So this is what we call the second and third generation of matter. And in each of these generations, there are basically identical copies of the first set of particles with the same properties but different masses. So, for example,
that's the spin. The mass is how the red, blue, green. So they're picking up the same copies of the same photons, but at different energy levels.
Electron has a sort of heavy version called the Muon, which is identical to the electron in every way, but has a mass about 200 times larger. And that's going to be an important thing to remember when we get a bit further into the event.
Free energy.
There are also a bunch of forces in the standard model. There's the electromagnetic force, which is carried by a particle called the photon, and that's a force where a lot of work was done on that, understanding the electromagnetic force at the Royal Institution by Michael Faraday in the 19th century.
That's over 100 years ago, and they still staying with all of that same stuff, like light is not a particle. Well, coming from the sun, just think about this. Coming from the sun is particles. Those aren't just nothing. They claim there's a vacuum in space, there's no particles out there. There's a ton of particles. Every one of them is magnetic, and that's all there is photons and electrons, and then they turn into molecules and atoms and so forth. And that's just, it's loaded, it's saturated space. So we're spinning through a soup of electrons. That's why our outside atmosphere, the ionosphere, is loaded with electrons, because we're scrubbing our electrons into their electrons that are forcing it down into our outside field. And that accounts for all the northern lights and, aurora borealis, all that business. All right, so here we go.
And there are two other forces, the weak and the strong forces, which are the strong force responsible, as I said, for holding quarks together in the nucleus, and the weak force responsible for basically when particles transform from one type into another. So when particles decay, it usually takes place through this weak interaction. And then to complete the picture is the Higgs boson, a particle that's connected to the reason that some of the particles in this table have mass. And that was the sort of, discovering the Higgs was the big triumph of the LHC back in 2012. So that's sort of basically all of particle physics in hopefully quite a short space of time. But there are lots of reasons for thinking that the standard model isn't the end of the story when it comes to understanding the physical stuff in the universe. Thanks to evidence from astronomy, we now believe that the visible material that we see when we look up in the sky only represents a tiny fraction of the total energy matter content of the universe. The universe appears to be dominated by two substances known as dark matter and dark energy, which are really just sort of words to cover our ignorance. We have no real idea or evidence so far what these things are.
I just showed you what they are. And the dark matter and dark energy is the black particle that won't go through the accelerator. And that's, I believe, it's just so massive that if you tune the accelerator correctly, which Rod did, he brought it down to a point where it was so close to each other, the venturi, that only the white could get through there. And that's what causes separation. And when they come back together, the violence is just unbelievable. And this could be done in a device, like a pocket device almost, that would run a car, or something a little bigger might run your house, totally off the grid. You wouldn't have to be plugged into any servicing facility. You'd be able to carry them around your pocket. Everything could be powered by a tiny, because you could make these lasers so tiny now to do what I was just showing you, to collect that energy, that it could be like in a ring. You could actually have it like on a ring or a bracelet to power almost anything. If what I'm saying is correct, and it's 200 times increase in energetic value, and we can do it with CMOS chips and so forth, which we can. I mean, there's no question we can. You've seen it. No question it's being able to be done. It's a device, and now it's a system of, we have to have engineering and to create a device or multiple devices, and they should be energy neutral. I mean, well, there won't be any carbon, there won't be any emissions of any gases or anything. There's just going to be particles that were divided and put back together, and we pulled some of the energy out as that process was in the middle. All right, so here he goes again. They have no idea what they're looking at this point, because they're working with billions of particles at a time, which creates a garbage dump. They're digging through it and they're finding fragments of stuff, and they're trying to put together a model, and they're never going to be able to do it because it's just too much information to dig through to figure out what happened, because they don't know what they started with. We started with light. We didn't start with 100 billion particles.
What these things are. In particular, we'd really like to understand what dark matter is, and this is finding a particle that could explain dark matter is one of the big objectives of the Large Hadron Collider, as well as a number of other experiments around the world. Another reason why we think that the Standard Model isn't the end of the story is to do with the mirror image of matter, something known as antimatter, which is sort of beloved of science fiction movies. And so we know that in the Standard Model, every matter particle has a sort of mirror image, a corresponding antiparticle, which is identical in every way, except it has opposite charge. So, for example, the electron has an antipartner, which is positively charged, which is usually referred to as the positron, but also as the anti-electron. And the same goes for all of the particles and the matter particles in the Standard Model. Now,
all right, I believe all they're talking about is when I showed you the photons back to back, they're talking about spin, and spin is related to what's on top and what's on the bottom. Whether the white particles at the top or the white particles at the bottom, that's the spin, and that creates an identical set of particles with an opposite charge. That's what I believe.
Now, the big mystery comes when we think about the very early universe, and what we believe happened at the Big Bang was that in the first sort of millionth of a second or so, huge amounts of energy were converted into matter and antimatter. But because in the Standard Model there is a very precise symmetry between matter and antimatter, we would have expected equal quantities of these two substances to be made, which would have meant that as the universe expanded and cooled, they would have annihilated each other completely. So they would met up, annihilated, and left us with a universe with nothing in it. So the fact there's stuff in the universe is again a big mystery, and another reason why we think there's more to discover beyond the particles that we already know about. A final...
All right, the key here is that those two particles have come back together. The positive and the negative particles, which they say was created at the Big Bang, which that's a whole other issue that we're going to have to deal with later. But if all those particles had a positive and a negative and they came back together, well, they did. But they came back together, and we never knew that the dark matter came back to the white matter. All we could ever see is the white matter, because the white matter is the only thing that radiates. You're never going to see the dark matter. Dark matter is just a puller, it's a sucker, it's a gravity, it's the muon, it's the 200 particle holder. It's a heavy, strong force. So anyway, that's my 10,000 words. Go ahead here.
The problem that I'll mention, I described these 12 matter particles to you, 6 quarks, which are the things in orange here, and 6 particles called leptons, which include the electron and the muon and the neutrinos. And we don't really have a good explanation for why we have these 12 particles. They seem to be, there are these patterns that repeat as you move along these columns, a bit like sort of the periodic table as it was understood in the 19th century, which perhaps suggests some deeper structure or some bigger picture which might explain where these things come from. But again, at the moment at least, we don't have a good explanation.
Yes, we do. They're all electrons. If you just take the electron flood theory and start to look at it with that set of eyes, every single thing, there's not a single thing that doesn't make sense anymore.
For why these particular matter particles exist, and it's something we'd like to understand. So that's why we think there's more stuff to discover, and that's and finding evidence of new physics, new particles, new forces is one of the key objectives of the LHCb experiment. Now, the B in LHCb stands for beauty, which refers to one of the 6 quarks. In fact, it's the 5th heaviest quark. It's a negatively charged quark, a sort of very heavy version of the down quark that you find inside atomic nuclei. And at LHCb, we study these beauty quarks at very high precision. And in particular, the LHC is a great place to do this because when protons collide at the Large Hadron Collider, you have a very good chance of making these beauty quarks. And LHCb actually records billions of these particles every year, which allows us to do lots of very interesting studies of how these particles behave, in particular, how they decay. Now, to understand why these beauty particles are interesting, we have to sort of take a little step back and actually think about how modern particle physics conceives of what a particle actually is. And so one of the surprising things, I suppose, given the name of the subject, is that particles are not actually thought of as being the fundamental ingredients of the universe. What we actually think of as being the fundamental ingredients of the universe are things called quantum fields.
All right, the quantum field is nothing more than it's the magnetic influence that these magnets control. So if you took a couple of bar magnets, all right, everybody knows how bar magnets work. Here's one that is one of my particles, right? And here's another one that has its field going against this one. They won't go together. Watch. This is what's happening. They're pushing each other apart. You see that? That's what's going on where it's push to shove. Now, if you had them back to back, side to side, they would snap together here like a photon. And then it would become fairly stable. Now, let's go back and look again at what he's talking about, fields. So we just saw the field, all right? This has its negative side, which is the push side, facing this push side. So they oppose each other, and they bounce, and they will spin, and they will do all kinds of gyrations. And that's what happens with light. We've seen this, is pretty obvious. Now, let's see what they have to say about the fields. Okay, he's talking about fields, not particles. Well, the particle makes the field. It's just a magnetic field surrounding the particle. And I think I showed this, or I'll show you right now. All it is you have particles that have, I showed you the black and the white in the particle, right? Okay, so this is basically, you have the black side and you have the push side. You have the attract, side, and this one here has the same thing. So what would happen if I came close to it? It would push it away. That's the push to shove. That's the field, and they don't understand that the particle is within the field. And one side's black and one side's white. The white one pushes, the black side just attracts everything. So here we go. They're going to talk about their fields. Okay, again, I'm saying particles, they're saying fields. Here he goes.
Is that particles are not actually thought of as being the fundamental ingredients of the universe. What we actually think of as being the fundamental ingredients of the universe are things called quantum fields. which are sort of invisible fluid-like substances that fill all of space. And that's a sort of hard thing to picture. Well, I mean, we've all experienced the effect of a field. If you've ever held a magnet next to a piece of metal and felt it sort of pulling on that piece of metal across a gap, you're feeling the effect of a field. And that,
all right, that's a pull field, yes. And there's also the push field, which I just showed you.
case, the magnetic field. Now, in the standard model, every particle that I've described to you is thought of as a little quantized disturbance, a little ripple moving about in an associated field. So, for example, the electron is actually a ripple moving about in something called the electron field. And the electron field is everywhere, it's throughout the entire universe, and each electron is a little ripple moving about in it. And the same goes for the beauty quark, or for photons, or for gluons. They all have an associated field.
I go along with
So in a way, what we're really studying at the Large Hadron Collider are these fields that are always there, that exist in the vacuum at all times. So
let me just show you something. He's talking about looking in space for fields. Like I said, I work with Rod Warren, and he did the light experiments, but his nephew, Dylan Carpenter, sent me something the other day. I still don't know what to make of it, but I'll show it to you. When you're talking about fields in space, you want to see some fields. I'll show you fields. Remember, this is a smartphone. This is no big fancy thing at CERN. Everything is a dipole. Somehow, I don't know what he's using. He's got some kind of app that shows the field effect of the different polarities. And you can see, there's no question, these are entangled fields of polarity. And there is the black and the white particle, like I was showing you. That's like a gigantic electron. What it's doing in space, I have no idea. This is brand new stuff, no clue about this yet. And it's got me freaked out, I got to be perfectly honest with you, because this is just one of a bunch of shots. And the blue indicates a more intense reaction, some heavy duty particle reaction there versus the yellows and the green, I mean the reds. And look at this. This thing here, this blows me away. I don't know what's going on out here. I have no idea. No idea whatsoever at this point. And these are the kind of things that I'd love to see somebody look into. But you can see everything there is a dipole. Somehow he's got some kind of software that can discriminate the intensities and value them and create what you're just looking at. I don't know what else to say. Everything's a dipole, though. I mean, everything's a dipole. And that's my theory anyway. I knew that right from 50 years ago. You can't have a gigantic positive nucleus and a couple little floater electrons, and they just pop together. Anyway, let's go back to the Royal Institution. Okay, so the electron field is everywhere in space, and I agree with that, and that's all the particles are. And every time light moves through those, it pushes back against the light moving that way. So light can change speeds. I've shown that too. Very, very obvious.
Where it's throughout the entire universe, and each electron is a little ripple moving about in it. And the same goes for the beauty quark, or for photons, or for gluons. They all have an associated field.
All right, and every time another particle hits that field, it can slow down. That's what's happening with the light that's coming to us from these distant stars. We have no idea where things are in space now, because the space is littered with particles, and we always assume the light just does not change speed. Well, it does change speed, and the more stuff that's in front of it, the more speed change will happen. So we have to determine where is it space densest, why is it, we got a lot to learn about where things even are in space right at this point, because if we didn't understand these were particles that have fields, which they do seem to understand it, I just can't understand why they don't realize that light will interact with these fields. It's very, very, very obvious to me.
So in a way, what we're really studying at the Large Hadron Collider are these fields that are always there, that exist in the vacuum at all times. So to try to explain what we do at LHCb, there's basically two ways, broadly speaking, that you can look for signs of new physics. And one is a sort of direct approach, where at a collider, say, you have two particles, you give them lots of energy, E, and then you collide them with each other. And what you can, if you have enough energy, what that can do is you can excite one of these fields and create a ripple in it and create a particle. So this is how the Higgs boson was discovered, for example. You smash protons together, the Higgs field wobbles, and you observe this particle called the Higgs boson.
Let me just show you something so that you understand what we did. We forced the photons to crush themselves, creating the particles. When they came out the other side, we could see the Higgs bosons all over the place. The Higgs fields, I'm sorry, because the particle, when it crashes back into the general matter at a speed that it can be reabsorbed, it just creates a spinning field of particles. Let me show you the Higgs, because that's, they will. Okay, these are Higgs fields, and after the venturi, this bit of white is where it's nothing but a raw electron. And then they crash into at an exact distance, and then they spin like crazy. That one there, I think, is a reverse spinner, and it created something that is almost, well, it's nothing I can tell you about. That's a Higgs field. That's a Higgs field. This one here is not, but it has some kind of structure. And when it hit this Higgs field, it did that. What that is, I have no idea. Other than that, everything else is pretty consistent. These fields are very obvious, and the particles that we see are very, very obvious. And they're the same particles. These are the white showers and the black, and we see the electrons, and we see them in green, and we see them in red. Like this is a green electron. Same thing. It's identical to the red, only it's much more powerful. And we actually have them going in both at the same time. And you can see how much more powerful the green is. It overwhelms the red drastically. And with people that are going to be doing the experiments, I want them to be doing experiments like this, side by side, different lasers, different colors, through the same slit. We can see that the green is now interacting. Think about this. What happens when the red comes through? It creates disturbance with the gases that are in the air. Those start to glow. Now, you would expect the red to be up this way and down this way. Well, the green takes over and pushes the red below its laser line. It's pushing the red down. It's saying, all you little red particles, get out of the way. We're the tough guys here. And they come through, and then they concuss out here. So they would not have concussed until they were out here, except that the red created a bunch of gooey little stuff right here. I would have expected, and see some red is pushed way up, even up into here, and then of course we have the same particle structure as the red. And I believe I showed you the red, but I will again one more time. Well, let me just show you what happens with, let me regain my thoughts here, hold on. Well, here, let's just look at this. This is the light spinning. I don't know if I show this or not. I get a little lost in these presentations. I've been doing so much of it. We need to get this understood. That's the particle. This is single slit. This is not double slit. These are not interference flappy waves going side to side. This is a spinning particle. That's a drill bit. Spin, spin, spin through a venturi, forcing the field to crush here, field effects. The black particles go around, the white ones go through, they create the showers, and they spread out, pushing each other away from each other because they don't want to be next to each other. That's what the interference patterns are. Everything really needs to be started over again, looking at things as this electron flood nature, where you have a black and a white ball attached together, creates the photon. And here they are. Let's see where they are. All right. And you would never see this. You'd never know that. Nobody ever saw this before. And the reason they never saw it is because they've never used this. Well, CERN has seen the particles, but they didn't know where they came from. They just knew it was all in a big ball of a mess. We know that that's light. That's light from a red pulse laser. It's just shooting its way through, having a nice day, and then all of a sudden it reaches this venturi. And just prior to hitting the venturi, they start to illuminate and glow quite a bit and make this box. Here they're not quite so boxed up here and not quite so illuminated. You still have them sort of flattened out, and here you have them twisted this way. You see they're twisted this way here? Like a little Oreo cookie. And then they twist sideways. I can't account for any of this stuff exactly yet, but I know that they're stacking up against each other now, and the whites are pushing the whites. And then they're squishing in until they become like this. And at this point, that's what we got. And then they explode right here at the venturi. And at the venturi, they separate. And I show that very, very completely. There's no question. And there they are separated. Fission, fusion. What's in between is raw energy. And that is the energy we need. It's 200 times more powerful than when it started. I say that's free energy, and I say we can do that with something handheld, basically, to run a house, a car, whatever you want. And you never have to put any gas in it. Do nothing whatsoever. It would just keep running itself and repower itself to create the laser, to create the division, to create the receiving of the raw energy. All right, and then you take some of it, you feed it back to keep the cycle going. This takes no power whatsoever. This is nothing more than a static, solid device run by a laser, and then a solar panel over here to collect the extreme energetic output. And then you run into batteries, a rectifier, all kinds of things. And then you could have a little device that you could slide it between AC and DC and 120 volts, 240 volts, a number of cycles per second, anything you want. Once you get these raw electrons, you do anything you want with them. Let's see something cool. Look at this. These are Higgs on the move, I call it. Well, what Rod caught here was the Higgs exploding as they concussed, and this one here pinched between two other particles and pinched it and turned the red into blue. And you can see it's like expanded, and then it squirted out another one, and it's coming back down to the red, but it's gained more energy. Now, I don't know if you could put this through an additional venturi and re-up the power. I have no idea. Once I saw that sort of blew me away. He sent me stuff that just, well, you can see it. I don't know if it blew you away, but it was damn sure blew me away. And that is the particle right there in the very center. That is literally the source of the spin. And as it comes through, it pushes all the other particles away, and they spin like crazy around them. That's what a Higgs field does. And it's because the light is spinning. And it's spinning fast, very, very fast. Now, just in case they don't show the Higgs fields, this is what they look like, just what I was showing you. Now, simulated Higgs event at the LHC. And this goes back to 2014, 2015, right in that area. And from them, that's all I've ever seen is doodles. I've never seen actual events. And what I'm showing you is the actual events. These are the ones I'm showing you are nobody's artist rendition or a bunch of little doodles. And I'm showing you ones that are down here, and they're the exact same patterns as here, but they're shooting gigantic particles together, creating the same sort of fields. Yes, absolutely. But with our fields, we're down into the range of subatomic photonic. And then it's photon fission, which is nuclear fission. It's the tiniest bit of the nucleus, and it reassembles itself back into fusion. Okay, so you've seen the Higgs fields. Now, here he goes. He says the Higgs fields wobble, and you observe this particle called the Higgs boson, which I just showed you, those fluffy, big, round disks.
Now, this approach is a great way to discover new things if you have enough energy, but you're limited by the amount of energy you can put into your collision.
Exactly. Here's the problem. All they're all they're doing is hitting two particles head on and hoping for the best. We're forcing them to snuggle up together so much that their fields separate and the particles separate. And I always found out that they're using brute force. And I'm going to tell you something. I always found out that a nice firm hug worked a lot better than beating them up. All right, so here we go. We're going to see about this collision.
So Einstein's famous equation says that energy and mass are equivalent, E equals mc squared. So that means that the maximum amount of mass you can create, the sort of heaviest particle you can create, is limited by how much energy you can put into your collision. So what if, for example, the particle you're interested in is too heavy for your collider to create directly? Well, the fact that these particles are all ripples in quantum fields gives you an alternative way to look for these effects. And this is where sort of the way LHCb works. So typically at LHCb, what we might be looking at is a beauty quark decaying into some other particles. So the beauty quarks, when they're created in the collisions, they only live for about 1.5 trillionths of a second, and then they decay into other particles. And this decay will take place through the standard model forces. So you have a bunch of forces that allow that decay to happen. And you can calculate very precisely, in many cases, how often a certain decay should happen, or the sort of what the particles that come out flying out from the decay should look like, what the angles should be, how fast they should be moving. But let's say that there is another force of nature, say a fifth force that we've not seen before. Well, even if we can't create a particle in that force field is still there. It's still there in the vacuum, and it can provide an alternative route for that decay to happen. So it can subtly affect, for example, how often a particular decay may take place.
All right, you see what he's talking about, this new quantum field down here? It's coming around, the particle's not coming standard through the normal standard model. It's a new quantum field for a decay. Well, that is what the bosons do. They go around.
And that's the sort of stuff we do at LHCb. It's measuring these beauty quarks, how they decay, comparing them to theory, and then seeing if there's a discrepancy. And if you see a discrepancy, that can be the evidence of something altogether new and exciting.
All right, let's see if we can see a discrepancy. Hold on. Okay, the reason they're calling these beauty quarks is because they're accelerated light particles. And they are just like that blue particle I showed you. Something's pinching it here, forcing to squirt out the particle that they're seeing. And they call these beauty quarks. But they're crushed fields. And that squirted out the particle, and then they see the decay going around, and they talk about this alternative decay. And that's exactly what I show you in our beauty quarks. And here's our beauty quarks sending their electron neutrinos, electron showers, and muons, and all this business around from the venturi. And all we had to do was cuddle that little puppy up nice and tight, and the black balls can't get through. They had to go around. They're 200 times heavier. All right, so she's going to continue on here about the standard model.
Something that we don't know, that could at the same time be the corporate for all of the things that we cannot explain with the standard model. So one example that I like to make is actually looking at the standard model itself. It has this weird structure with these 3 different groups of particles and these weird scales of the different particles. And maybe this thing that is responsible for this measurement is also behind maybe the structure of the standard model. It
is. It's the electron. The electron builds everything. And if you take a look at it that way, just start doing some calculations, do some thinking, look at the stuff I presented, and see if it makes sense. If it doesn't, we'll go on about our business. But I think it makes a lot more sense than what is currently thought of as the standard model, where you have big, gigantic protons and neutrons.
So that is what makes it interesting. However, the expert really here is Ben, so I think I now will let Ben tell us a little bit more about what could be behind.
All right, we got a little commercial.
It's great. Thank you, Paola. Okay, so as Paola has told you, experimentalists have expressed cautious excitement at these results that Paola's been talking about. And I'm afraid I've thrown caution to the wind for the last 3 years, and I'm like really excited about these results. Not only the one that Paola talked about, which is the flagship measurement, and it's the cleanest prediction.
You know, I got to point this out. Every single one of them you watch now, they show the venturi shooting out the particles. Every single one of them, because CERN has seen this. Fermilab, you look at anything Don Lincoln has, he's got these behind him. Every one of these guys now. That's what we did 6 years ago, and I presented it to every one of them, and I showed all the video too. I showed all the pictures that we had this six years ago.
Of the standard model, and a very nice measurement. But there are also kind of 5 others which are sort of, to my eye, pointing in the same direction. So I've spent all my career looking for new particles and forces. I cut my teeth in the early days on looking for supersymmetric particles, which we haven't found yet. But 5 years ago, because of the kind of data that Paola's talking about, I kind of switched focus, and also because the Large Hadron Collider hadn't seen any supersymmetric particles, I switched focus to this kind of physics. So I'm going to tell you about another measurement now, actually done in America, different experiment, and it's a measurement of the muon's wobble, strangely. So the muons and anti-muons were involved in Paola's measurement, but this is a different measurement involving them. And it's a measurement really of the wobble of the spin. So the weird thing is that particles, apart from the Higgs boson, other particles behave like spinning tops. So this is a bit strange because you might want to think of them as points, but as Harry mentioned, they're not really points. There are some weird quantum fields and like quantum jelly throughout the...
No, they're actually particles, and they have a positive and a negative, and they do spin, and that creates the light, and that creates the push to shove as they bang into things.
The universe. And so how does this spin, really manifest itself? Well, if they've got charge, then spinning charge gives you a magnetic moment. And so muons, for instance, they have electric charge and they're spinning, so they have a magnetic moment. But the spin also imprints itself on the decay product. So if the particle decays, the energies and the angles of the particles will be affected by the spin of the decaying parent.
All right, I really couldn't understand what that meant, but I do understand a little bit about the spin, and it's related to the fact of the polarities going this way and that thing going through the air, and one of them hitting, spinning it, and then the next one hitting, spinning it. Now, why it does a right-hand spin, I'm not 100% certain, but they appear, the right-hand rule says if it's spinning this way, it goes this way. The curve goes that way, right-hand rule. So if the particle's going this direction, the spin is this way. And I'm not 100% certain of why that happens. I've seen one go backwards, but the only one. Anyway, if you could make sense out of what he was saying, good for you. I couldn't.
Okay. So let's have a look now. Hopefully you can see this video. Here's our muon. It's just like a gyroscope, so it's spinning. But if you put the muon in a vertical magnetic field, its spin precesses around some axis. And it's the measurement of the rate of this precession of the axis that this experiment is aiming at. So the experiment is called the G-2 experiment. We'll see a photo in a minute. It happened on the outskirts, well, just outside Chicago, in a lab called Fermilab. And actually, it also happened at a different lab in the States around 2000. And in around 2000, they found one of these discrepancies with the standard model prediction. Okay, the idea of this measurement is that...
I just want to interrupt. He's talking about Fermilab, and I have been trying to work with Don Lincoln at Fermilab, and I know he's busy, but I think I have pretty good evidence to show that we have something to contribute here. And at the moment, I'm not going to be able to get through to them. So if anybody would come on to this, and believe me, all I want to do is have somebody understand this new electron flood theory, but it needs to be looked at. And all I ever hear from anybody is, you get it peer reviewed, gets this and that, and you know, but nobody will talk to me about anything. So I will peer review what? So if somebody will give me the chance to make the presentation and look at what we did, I think we have a good chance of getting free energy. I really honestly do. And they do too, if we can do what I said, separate the muons and the bosons, I mean the muons and the electron showers, and then when they come back together, that's fusion. That is what they've been looking for.
You measure this rate of precession of the muon really, really precisely. And then you can also, if you do a lot of work, I mean, it's really a lot of work, you can make the theory prediction very precise as well. So
yeah, it is a lot of work because you're trying to come up with all these little doodles that don't have any reality function. I'm showing you in quick little pictures this exactly what they want to see, the muons, the electron showers. If you haven't seen them yet, I don't know what to say.
There's a lot involved in this. There are, you know, tons of people calculating different bits of it, and you know, it's all got to be checked. Some of it you can't even calculate on paper using first principles. So you can't even get a computer to calculate on, you know, after doing some paper calculations.
All right, I got to be honest with you. I don't see any reason to go too much further with this. Let me just show you for one last time what we did discover, and it is new physics, no question whatsoever. Okay, these are the radiation cones. And what do we have here? We have a muon neutrino and an electron neutrino. And I say that is a black ball, and that is the white ball. And they are attached together. And that together is an electron. That is my statement. And everything there is made of electrons. And because of the mass of an electron, 1,839 of these electrons would make up one proton. 1,840 of these black and white balls would make up one neutron. When this black ball and white ball is attached to another black ball and white ball, they are literally 2-bar magnets. They have a mass of, it's very, very small, and like I said, 1,839 of these make up one proton, so that's how small they are. When they hit our venturi, the radiation cone of the muon neutrino, the black ball, did not change. It stayed a black ball. The electron neutrino radiation cone turned into electron showers, the white particles, and here they are right below. Okay, this is them at the venturi. They came into that venturi looking like a black and white ball and a black and white ball together in a box formation. And when they hit the venturi, only the white particles can get through this tuned venturi, and you have to tune it to a certain size. The black balls are not allowed through. Apparently this is what we got. And again, this was an accidental thing. This wasn't something we set out to do. But when, you know, my background is in this. I've been 50 years doing this, and I show this over and over and over, and that's just the way I'm going to do it. This 50 years ago, this was my paper submitted to say that there is no such thing as a solid positive nucleus. It's impossible. The forces, it can't happen. It had to be dipoles. And then I also stated that that light is electronic vapor. 50 years ago. And that's written in my notes. I have it all documented. Light is electronic vapor. That's all this is electronic vapor. Fission, fusion. In between, raw energy. 200 times what we started with. To me, that's free energy.